Thank you ever so much for the invitation to come tonight. I'm really thrilled to be able to talk for the Royal Institution, if not at the Royal Institution, as much as I'd have liked to have been there. I'm in my slippers right now and I've just had a cup of tea. So I'm hoping that you're doing the same as we go through about 1 billion years of history. And we're going to be talking about lots of mysteries. I'm going to be talking to you tonight about lots and lots of big discoveries in astrophysics, and one of the biggest discoveries that framed my childhood when I learned about it, which was the discovery of Tutankhamun's tomb. So here on the left, you can see Howard Carter and Lord Carnarvon, and they've just chipped away the first part of the tomb door that's not been opened for thousands of years. And as Howard Carter held up a candle to the hole, Lord Carnarvon said, "What can you see? What can you see?" And Howard Carter just simply replied, wonderful things, and everywhere the glint of gold," which is a wonderful story. And finding out about our history, understanding these great discoveries was enough for me when I was a teenager, and I'm still interested in it today. But my head was turned when I learned how much we didn't know about physics, and then later how much we didn't know about the history of our universe. And so tonight I'm going to be talking to you still about history, still about where we come from, so something we're fascinated by as humans. We want to always look back, always ask who we are, where we came from. And this starts even when we're children, just as my fascination with Egyptology did. You are fascinated by lots of different things when you are a child. You're fascinated with archaeology and history, like I've just said, uncovering the tombs. You're fascinated with dinosaurs. Dinosaurs are the best. And of course, there's the one that caught my eye, which is space. All three of these are like the holy triad of children's passions, right? And so tonight we're going to be looking at this. We're going to be blending space and history, and sadly not dinosaurs, though I am actually wearing dinosaur earrings, I've just realised, so that's nice. So I want to start tonight properly off by talking about what is light. We're going to be talking about light an awful lot tonight. We're going to be talking about first light, so when the lights first came on in the universe, but we're also going to be talking about light as a diagnostic tool. So how can we use all the different types of light to diagnose our universe, as it were? There's lots of different types of light. The one we're familiar with is the optical wavelengths. So those are the wavelengths of light currently entering your eye, onto your retina, so that you can see me waving at you. There's lots of other different types of light that we're used to. So, for example, radio light, the radio wavelengths of the spectra, because light is a spectrum. And so it goes from very long wavelengths to very short wavelengths. So with radio wavelengths, we bounce them off the atmosphere of the atmosphere of the Earth, for example, and they'll bounce back down, allowing us to cover really long distances with our radio. There's the infrared radiation, which we can use, for example, to track criminals as they run away on some American cop series or something. We can use UV light to decorate ourselves nicely for when clubs used to exist. Or, for example, if you're watching CSI, they can also be used to find gruesome discoveries of where you can find the bodies. And then the last one we might be familiar with, for example, is X-rays. So when you break your arm, for example, the doctor might first say, "Oh, yes, that's definitely broken," using optical light to notice that it's at a completely wrong angle. But you'd be a bit worried if they didn't also use X-rays to diagnose exactly how it's broken, exactly how to fix it. And so with light acting as a spectrum, as it is, as I've just gone from small wavelength to long wavelengths, we use the same kind of spectrum to diagnose our universe. So here we've got Centaurus A, a galaxy, so you can kind of see fairly big compared to the stars. But when we actually look at it in radio waves, this galaxy is revealed to its true self. So we see these incredible radio waves, radio lobes, ejecting material out of the central black hole. And if we just had an optical telescope, we'd say, oh, well, that's about it. There's certainly no sign of a black hole the way we're looking at it now. But if we switch this radio telescope on at the same time, then suddenly what we can see is a great big sign saying black hole here. So using all of these different wavelengths to find out different things about our universe is what we do on a daily basis. These are very different types of light, as you've probably noticed from the different kinds of, well, different types. It's all the same thing. It's all the same light, but they're all very different wavelengths. But the one thing they really have in common is that they're incredibly, incredibly fast. So the speed of light is around 300 million meters per second. That's really, really fast, which means that when I wave at you, you don't really see any lag at all. So if I wave at you, then hopefully you're sat on your sofa or your beanbag or whatever, and you're waving back because you can see it almost instantaneously. But now let's imagine that we were actually on the moon. So on the moon, what would happen would be you would have a signal going. So you would wave at your friend on the moon, and they would wave back. And because it's only 1.3 seconds in light time away, you're quite happy with that. Your friend's waving back, and yeah, there we go, little friend waving back, and so your friendship stays intact. But if we then go on to the next slide, sorry, and I've got to go on to the next slide, so it's going to take me a minute. Now let's imagine that our friend was on the moon, on the Mars, sorry. And if you've got the same kind of signal going towards Mars, then you can wave at your friend, but it takes 4 minutes for the light to actually get to them, and another 4 minutes for it to get back. And so by that time, you're pretty sad because you think that your friend has just completely forgotten about you. Just left my Duplo person somewhere there. Okay. Now, oh dear, sorry, I've just gone on too far there. There we go. Okay, and now you might have heard the very QI-able fact that the light that we see from the sun is actually 8 minutes old. So I've got a pretty giant sun here, but I can't actually fit it in the thing. But anyway, so light takes about 8 minutes to get to the sun, and it takes about 8 minutes to get back, by which time you've just lost all hope that your friend's even seen you, and the friendship's probably broken. Now, what this means is that because the light takes 8 minutes to get to us, we are seeing the sun 8 minutes ago. So anything that happens on the sun, whether it's your friend waving, whether it's a solar flare, whether it's a supernovae, we will only learn about it 8 minutes later. Now we can extend that even to a larger scale. So let's say that we were going to wave to our alien friend in a completely different galaxy, a nearby galaxy. Now the light, because this galaxy is so far away, the light would take an incredible 2.5 million years to get to that galaxy, and another 2.5 million years for our friend to wave back, by which time we're not just really sad, we're actually also really, really, really dead, which is a problem. Now, this again is really great because what it means is that we can look back in time. We can look back 2.5 million years ago and see Andromeda or whatever nearby galaxy it is. We can see our nearby galaxy as it was 2.5 million years ago. And also, equivalently, our alien is actually not waving. If they're observing us right now, they're not observing us watching a Royal Institution lecture. They're actually observing the Earth 2.5 million years ago. So what they're seeing is one of the first ancestral branches of humanity, which is pretty crazy, right? But this is exactly what we're doing on a daily basis in astrophysics. The longer light has taken to get to you, the farther you are looking back in time. So we can really use this to fill out the timeline of our universe. So here we've got a timeline of about 14 billion years, because we think that, give or take, that's roughly how long the universe has been knocking around for. We know lots about our Earth because we can just look out the window for a start. We can do lots of tests on it, so we can put that on our notice board and be pretty happy that we know lots about it. As we go a little bit further back in time, as I've said, a few seconds away is the moon, about 4 minutes away is Mars in terms of light travel time, but we can still find out a lot about them. In fact, there's plans to put boots on the moon, boots on Mars. So it'll be that we're even going to have humanity back on these structures at some point soon. And then we've got the closest galaxy to us. That's about 2.5 million years away, Andromeda. And even further, we can look back even further with incredible telescopes and see galaxies from millions to even billions of years old. And indeed, the Hubble Deep Field is a photograph which was taken by the Hubble Space Telescope. And what it did was it stared at a tiny patch of the sky, about a tenth of the area of the moon, a patch of sky that big, and it stared at it for a while. And what it found was deep, as in very deep in light travel time. It found galaxies all over that patch of sky. So just thousands of galaxies, and I'll do a bit of a larger image of that later. But the point is, we can really push back to about 1 billion years after the Big Bang, maybe 800 million, but it's a bit contested, so 1 billion years after the Big Bang. And we can even jump much further back now. So to go right to the start of this universal timeline, we know quite a bit about the Big Bang now. We've got a lot of theories for 100 years now, all about how the universe started as an infinitely dense point and expanded out a huge amount to the universe that we see today. And we've even managed to measure the radiation from this Big Bang, which I'm going to go into a lot more in a minute. So my point here is that even though this is not remotely to scale, the point I want you to take away is that we've managed to fill out huge chunks of our timeline, and we can be really, really smug about that. But there's a whole era missing of about 1 billion years in length. And we call this the era of the first stars. So if we look on a bit of a prettier image here, it's kind of just saying the same thing, which is what happened here? What happened where the question marks are? We know that there was a Big Bang. We know that when we look around us now, there is incredible diversity, incredible complexity in terms of structure. How on earth did we go from one to the other? And so let's have a look here. There we go. As I've just mentioned, we believe that there is a Big Bang. Now, the Big Bang, as I've just mentioned to you, is this infinitely dense point expanding out, which is entirely preposterous. I say it very easily in one sentence, but actually to believe that there is a Big Bang, to understand why we believe there is a Big Bang, is a whole different thing entirely. And so I'm going to start going into a little bit about the evidence for the Big Bang. Because it is important, because if there isn't a Big Bang, if there isn't a start to the universe, as some people did believe 100 years ago, they thought that the universe was infinite in time, infinite in space, and so forth. There wasn't the first of anything. So if I'm going to talk to you about first light, the first baby steps of the universe, the first stars, then there's not much point me doing it at all if there wasn't a Big Bang, if there wasn't a first of everything. So the first thing I want to convince you of tonight is that there was a Big Bang. And the first piece of evidence that we can give for this is how the surrounding galaxies are moving. If you think back to the last action movie that you watched, so probably starring Bruce Willis and Arnold Schwarzenegger and Sylvester Stallone, I'm not sure. But imagine that there is a gigantic explosion. Now, what you see is you see the people, you see the debris, you see the buildings, you see it all flying apart. You see them all moving away from each other as they're blown away, hopefully not blown apart, blown away by these incredible explosions. And what we actually see in the surrounding galaxies is a very similar thing. So as you can, I'm still not sure if you can see my pointer, but it doesn't matter. Hopefully you'll see the red arrows here. And the point is that when we measure how all of the galaxies around us are moving, they're all moving away. And we could be pretty sure about this because how these first galaxies are moving, we can find out by looking at the light they emit. So here, what I'm showing you in the colour is an example spectrum, we call it. So all of the different colours of light that a galaxy might give out, all of its stars give out at the same time. And normally you would expect this spectrum to be quite full, which means lots and lots of colour, so no gaps. And when you get gaps in your spectrum, as you can see here with the dark lines, we call those absorption lines, what that tells you is that there is a certain chemical element. So let's, for argument's sake, call it calcium for this demonstration. If there's calcium present in that galaxy in large amounts, then that calcium likes to absorb wavelengths of very, very specific wavelengths specific to that element. And so what you'll find is you'll find absorption lines, and it's kind of like a barcode which tells you exactly what the ingredients are. So we can look at this spectra on Earth and we can tell that there is calcium present in that galaxy. Now, if a galaxy moves away from us, what happens is that we perceive the light from that galaxy to be what we call redshifted. We perceive those absorption lines to be moved up the spectrum to the red waves, so redshifted. And as well, if the galaxy is moving towards us, then what we do is we see those absorption lines shifted to the blue end, and we know that's not where that's not where they are meant to be, because we can put calcium in a laboratory, we can chuck a whole load of light at it, and we can figure out which photons, which wavelengths it prefers. So this is a really cool way of figuring out what speed and what direction, etc., all of these different galaxies are traveling at. And like I said, apart from Andromeda, which is moving towards us on a collision course, yay, it's the vast majority of these galaxies we see moving away from us at very, very, very high speeds, which is an indication that a big explosion has happened. And you can't really get a bigger explosion than the entire universe starting with an incredible inflation period. The second piece of evidence for the Big Bang is the radiation that it leaves behind. So it's got a very grand name, the cosmic, meaning all around us kind of thing, big scales, microwave, meaning microwave wavelengths, background, meaning it's not in your face, and radiation. Okay, so as the universe is expanding, then the radiation of the Big Bang, it moves to longer and longer wavelengths. So this radiation is everywhere. This radiation is pervading the whole universe. And as it goes larger, it loses energy, it loses energy, it loses energy, until eventually that light gets shifted straight out of the visible wavelengths and into something much longer, the microwaves, for example, the radio a little bit. And interestingly, if you are old enough to have had an analog television when you were young or even older, then you will know that when you used to tune the stations between the different TV channels, you got a hissy kind of static, like a s. And interestingly, a significant portion, a small but their portion of that static noise was actually from the cosmic microwave background. Good. I've just realised my video wasn't on. Sorry, so you couldn't see me gesticulating wildly, but never mind. And what we can see with the telescope is not just this static on the television, but you can actually see the cosmic microwave background in full glory, in full colour. So we have these space telescopes that have been for the last couple of decades really filling in this information. So the point I want you to take home is that we have seen this, is that the Big Bang, there's more than that in terms of evidence, but the two big pieces for most astrophysicists is the movement of the galaxies and the fact we can actually measure the leftover radiation to exactly what is predicted by Big Bang theory. And so even though the idea of a Big Bang is completely preposterous, it's also completely acceptable and completely believed pretty much within mainstream astronomy. So that means for us is that there were first stars, that there were these first entities that we want to find out about. But one question that is a really good question to have that you might be too afraid to ask is, well, hang on, if there was a Big Bang, that's already completely ridiculous. So is it possible that the first stars, the first galaxies just popped out of that Big Bang, completely fully formed? Is it that we don't really need to find out how those entities got created and how they formed, but actually that the first stars just went pop out of the Big Bang? Well, we know from understanding the physical mechanisms behind the Big Bang, what was going on. We know that just after the Big Bang, it was incredibly, incredibly hot, incredibly, incredibly violent. And so you have all of these photons going all around and basically messing up building anything taller than anything greater in size than a helium or a hydrogen atom. So a hydrogen atom is made of just, for example, one proton. So if we use it like that, and helium is made from 2 protons and 2 neutrons and some electrons. And what I always imagine is that if you are in a room of sugar-crazed toddler, then you can try and build a bigger tower, a bigger atom, but it won't be too long until you get your little friend coming along, cracking it down into its constituent parts. So while you might try to build a taller tower and you might succeed sometimes, it's really not so long until eventually you're just left with your basic building blocks. And that's exactly the same in the early universe. Try as you might build up lithium, but you'll end up with just hydrogen and just helium. And that's certainly not what constitutes a first star. So we definitely need to figure out how we got from a universe that was just hydrogen, just helium, all the way up to where you've got galaxies, you've got planets, you've got carbon-based life forms that breathe in oxygen. How did we get to all of that? So hopefully I've convinced you that there were first stars. And now I need to convince you about why we need to care about the first stars. So we're missing around 1 billion years of our timeline, which is a huge amount. And missing 1 billion years of a 14 billion year timeline is really equivalent to missing, for example, the day of your child's birth right up to their first day at school. So if you consider how much stuff happens in that time, it's a really formative time. And if we were to imagine our alien from Andromeda coming down to see us, and he wants to learn all about the human lifetime. So what happens in the average human lifetime? So average one, you start with a baby, you become a child, you possibly procreate, and then you enter the autumn and winter of your life. But if our alien flies down to Earth and only has limited time, limited research funds, is really tired, then they might only take samples, they might only photograph, for example, certain humans in certain types, and they might end up with incomplete data, which is exactly what we're looking at with the first stars. And it doesn't take too much imagination to think, well, okay, I heard that person talking about where babies come from, so maybe that's actually what's happening here. This model, it fits our data perfectly. Excellent job done. Time for a beer. And so our alien would just float off happily back to Andromeda, completely unaware that they'd made completely incorrect conclusions because of their missing data, because of them incomplete data. And as I've said, we're missing about that first billion years of life, which is equivalent to your first 5-6 years of childhood. And it's no wonder that as astrophysicists, we're kind of quaking in our boots about what's being missed. The next reason to care is because the first stars themselves are extraordinary. So I study them because I love them, because I find them absolutely fascinating, and because, to hark back to my Egyptological days, they are lost. So they are something that we can't look up in our backyard. I can't walk next door and talk to an ancient Egyptian. It's just not possible anymore. And they're different. So this is our sun. This is an incredible image of our sun. You can see some solar flares. You can see sunspots. We love our sun very much for many, many reasons. And for the first star here, I've had to kind of put an artist's impression, which was basically me just going PowerPoint artist's effects and making it look a bit fuzzy, because we haven't got a single picture of a first star. They're not around anymore, or are they? We'll talk about that later, but mostly they're not around anymore, so we can't take pictures of them. But we know a lot about them because, like I said, we can do the kind of maths of what the chemical cooling reactions were, how big a star could get, how small a star could get. We can do all these calculations. So to the best of our knowledge, these first stars were about 100 times the mass of our sun. Some simulations even think that they were up to 1,000 times the mass of our sun, which is a really, really huge amount. That's a really, really big difference. And it's very difficult to kind of imagine, but for the sake of the fun, it's kind of the difference between a red squirrel and a great panda. That's a huge difference in terms of mass, and it's what we are looking at with these first stars. And this analogy, stretched analogy, works even better because, like the great panda, which is on the verge of extinction, it's the same thing with our first stars. We think they are either extinct or on the verge of extinction. So definitely worth looking up. The reason we think that we can't see them around us anymore, that they are extinct, is if we look at the mass lifetime relationships of stars. So if we have our first star, they are really, really massive, and really, really massive stars guzzle through their hydrogen that they are fusing. So all of the fuel that gives out the heat and the light, they guzzle through that fuel at an incredible pace because they're just more gravity, more contraction, more pressure. And so they will have a short lifetime of, say, 1 million to probably nearer 100 million years, which is really, really short in terms of stars, because stars like our sun, they are like the friend that you take to a restaurant and they just pick over a side salad. They are very leisurely in terms of their consumption of hydrogen. And so they will last more like 10 billion years before they run out of fuel. And that's just about the lifetime of our sun. So our sun's nearer 9 billion years, of which it's halfway through, which is good. Don't like to think about the end of that half, to be honest. But it's also the time that Andromeda is due to collide. So rubbish time all around. But who knows? Maybe we'll have managed to get some kind of extragalactic movement by then. So we think that these first stars are extraordinary in themselves, but also because they're extinct. And more than that, they're not just contained in themselves, like very interesting to look at, and then we move on to the next thing in the museum. They actually change the universe in a way that no other star has managed to do in quite such a dramatic fashion. And they're very, very different in that they contain fewer metals. And we categorize our stars as astrophysicists in many, many ways because we like collecting things. And what we call these first stars are metal-free. And that is because they formed out of gas that is just hydrogen and just helium. And so I'm just trying to, so you can see the hydrogen and the helium on this image here. And every other element on this periodic table, you might be having PTSD harking back to your chemistry lessons right now from when you had to go hydrogen, helium, lithium, beryllium. As astrophysicists, we're really used to rounding up absolutely everything in our universe because huge distances, huge timescales, we round everything up. And so we've rounded up the periodic table too, because pretty much everything's hydrogen, helium, and then everything else we just call is metals. So sorry to any chemists that are present. But that's the way it is. And so if we go back to this lovely picture here, then what we're saying is that here we've got an arrow talking about how the stars evolved over the timeline of our universe. So we start off with just hydrogen and helium. And so we call these stars metal-free. These stars fuse the hydrogen and helium into slightly heavier elements like lithium, beryllium, carbon, nitrogen, oxygen. And as they explode, they send all of these materials flying, and then they can come together when the gas has cooled down. They can come together, and all that gas can come together, form a new star. But this time it's got a bit more metals in, so it's metal poor. And then we go on to the stage where our sun is at now, so the stage of our universe where we're producing lots of kind of sun-like stars, and they are what we call metal rich. So they've got lots of metals, and it's actually still just a small percentage compared to the hydrogen in the star, but it's there and it's enough for us to categorize it. I'll just flick through my lovely slides here. Yeah, okay, so as I've said, you have the fusion, lots and lots of fusion to heavier elements, and boom, you manage to take all of those heavier elements and seed the local universe such that the gas is no longer primordial, it's no longer pristine. It's no longer just hydrogen, helium. It's actually got carbon, nitrogen, oxygen. And so early in the universe, what we're looking at is, as I've said, just hydrogen, just helium, nothing very interesting to look at all. As I've mentioned before, with the cosmic microwave background, whereas very early on, it was, very bright. You would have probably seen it as well as, you would have seen it. As the universe cooled down to, say, 500,000 years after the Big Bang, then everything was very dark. Everything was incredibly boring. And so if you had your TARDIS and you went back in time and you saw it, you'd be really, really bored because this is what you would see. It's not my presentation broken. But somehow we get to the point of seeing galaxies all around us, just like this. And as I promised, this is a slightly larger version of the Hubble Ultra Deep Field. And this is on my in my kitchen. It's on the big canvas on my kitchen wall because I just love it. I can stare at this for hours because if you just look at some of these spirals, like on the right hand of the image, you've got this yellow gorgeous spiral. You've got really flat spirals looked at from the edge on. You've got orange ellipticals. Every piece of light on here is a galaxy. which, apart from the odd interloper star, but the vast majority are galaxies, which is just fascinating to me, because this came from a postage stamp size, so less than a tenth. What is it? I think it's, if you hold out your thumb and you close your eye, that's about the patch of the sky that's covered. Even smaller than that, about a tenth of that, that's covered by this kind of structure. And the only reason that this can happen at all is because you have the metals to form them. And it's only because of the first stars that we created those metals, and we were able to then go on to forming galaxies and planets, and of course us. Okay, so hopefully I've now convinced you that there were first stars, and hopefully I've also convinced you that they were extraordinary and worth learning about. And what the aim of this game is, of course, is to go from a rubbish artist impression that I mocked up to an actual image, an actual learning about that first star. So how can we do this? Well, we can start by looking back in time. I'll take a drink for a moment while you read that terribly inspirational quote. I spent a long time at the start of this talk convincing you that as astronomers we can look back in time, which is a skill set you have to have on your CV. And what that means is that, of course, if you were on Andromeda or a nearby galaxy, then you might see one of the ancestral branches of humanity. Now, to turn that around, all we need to do then is we need to tune into light that has traveled so far to get to us. It's lost so much energy against the expansion of the universe, just like the cosmic mega background, that it's shifted from the shorter wavelengths into the longer wavelengths. If we tune into that wavelength, just like we tune into a radio station, then we might be able to see the light from this era of the first stars. And that's what we're doing. And this is just as crazy and just as real as, for example, if I was interested in ancient Egypt and the speed of light was much slower, then we could just use clever optics to look back at Egypt from where I am now, and I would be able to see them building the pyramids firsthand. So not a simulation, not what we think from the tombs and the writings, but actually see ancient Egyptians building these pyramids. And that's what we're doing. We are using the fact that light has a finite speed, how much energy it is, how we can tune it in. We're using all of that to actually see light from the era of the first stars, to actually see this era begin and how it progressed and ultimately how it ended and the second stars came along. Now, to do that, we can't unfortunately just use a handheld garden telescope as you've seen here. We use something called a radio antenna. And that's because the light has been redshifted so much. You can see here, so I was talking about redshifted, which will go to the longer wavelengths. So you're getting into longer wavelengths as it travels near the Earth. And so that's no longer in the optical part of the spectrum, that's in the radio part of the spectrum. And so what we do is we use radio telescopes. And here's one I made earlier. So this is an artist's impression on an amalgamation really of real antennas and the background of the Milky Way. And what this is called the square kilometre array. So this is the second big telescope in my life. I'll get onto the first in a minute. But it's very simple technology in some ways, because as you can see, this is basically what we call a Christmas tree antenna. Not just making that up for the festive season, but it is because they look roughly like Christmas trees and because we decorate them accordingly every December. And the idea of this is that we can put loads and loads of these antennas out, and we can tune in to the right wavelengths that we know that this light from the first stars is at the minute, because it's traveled so far to get to us. And we can pick up that radiation and we can learn things about the first stars. But how do we actually do that? Well, what we're doing when we're tuning in is we are taking the temperature of those first stars. We're taking the temperature of the surrounding gas at that time, actually. This is one way we can do it, one way you can find the first stars. So on the top here, I've got the age of the universe going from the left, which is very young, and going all the way to the right, which is present day. Now, on the left, what I want you to see is that before the first stars came to life, then we've just got a universe of hydrogen, of helium, of photons. And if we take the temperature of that gas, then it's very, very cold. There's nothing much heating it up. You can't see anything, so it's very, very cold. But what we can tune into specifically is that, as I've got a picture here between the blue thermometer and the red thermometer, is that we can tune into something called 21 centimeter radiation. And this is the radiation that is coming from the era of the first stars. What it is that when you have a complete hydrogen atom, so a proton and an electron, then that very specific makeup can produce a photon which travels off with a wavelength of exactly 21 centimeters, which by the time it's reached us, by the time it's been stretched, it's lost all those energy, it's at wavelengths of nearer 2 meters, which is why we use radio telescopes, because that's like the right wavelength for radio. So now let's look at what happens when the first stars come to life. So you have all this hydrogen pervading the universe. What happens is that this hydrogen starts to come together. It comes together closer and closer through gravity. It gets pushed together by constant gravitational pressure. And then suddenly, right at the center, you get this fusion. You get these first stars turning on. And it happens over here. It happens over here. It happens over here. One by one, lighting up the universe. So like fireflies in the night, just coming on like that, just switching on the fairy lights, if you will. But as these first stars come on, they heat the rest of the hydrogen that hasn't become a star. So there's still lots of hydrogen floating around, lots of clouds of hydrogen, and a bit of helium. And what these first stars do is they heat this hydrogen. And what we measure when we measure this 21 centimeter radiation is we measure a jump in temperature. And so when we measure that jump, we know that the universe is the light from that time is coming from a time where the first stars have come alive. And then as we go longer, so longer from the age of the universe to, let's say, 1 billion years after the Big Bang, what happens is not only do these first stars heat the hydrogen, but by now you've actually got the second generation of stars and you've got the first galaxies. And at this point, what happens is something called ionization, which I've got here between the red and the empty thermometers. What happens is the photons that are being emitted by these first stars and galaxies and everything like that, it breaks apart this hydrogen. It breaks it apart completely so that the proton and the electron are completely split. And so no 21 centimeter radiation at all can be produced. And what this means is that suddenly you can't measure any temperature of the hydrogen gas because it's just not emitting those photons anymore for you to pick up. So you have an empty thermometer, as it were, but that still tells us something. So even measuring when we get no reading of temperature tells us when these first galaxies have managed to ionize all of that gas. How big were they? How many there were to be able to do it in that time frame? Okay. So a bit more of a, just to hammer home what it is we're actually observing. I've got the same timeline here, but in red, I'm kind of representing all of the radiation that comes from this time and what we would actually observe. So with these radio telescopes, what we can do is we can build up a picture of all of that hydrogen across an area of the sky. So we tune it in, we tune in to exactly the wavelength, so about 2 meters that we're expecting this first light signal to come to. And what we observe at first is we observe the light from what's called the dark ages. So it's dark for an obvious reason, as I've said, because it is actually dark. The first stars haven't come on. So what we see is in our picture is we see a completely full picture of hydrogen, because there's tons of hydrogen. It's all held together. It's proton and electrons together. So there's lots of this 21 centimeter radiation. Lovely. As we move on, these first stars start to ionize and heat their local hydrogen, and it's what we call a Swiss cheese model. So I've got here's one I made earlier, and I was just telling the producers this stinks. I didn't realise I'm not going to use this as a prop again, but yeah, you get bubbles, and we call this the Swiss cheese model. Put that over there, and as the first galaxies come on, and the second generation of stars start emitting lots of ionizing radiation, so lots of these photons, not only do you get nice clean Swiss cheese like bubbles when the first galaxies come on, and the first black holes, actually you get a huge amount of radiation which makes very, very large, very, very wispy bubbles which coalesce very quickly, which overlap, and eventually you really kind of get your empty thermometer. So in the black here is an absence of 21 centimeter radiation, so you start to measure nothing at all. And what we can do with our radio telescopes now is we can reverse engineer this. So what we are going to measure, and what we are measuring, is this bottom row. So we are measuring all of these images throughout about a billion-year lifetime, the first billion years of our universe. We're building an actual home movie, so not simulation, but an actual movie of how this hydrogen is changing. And while that might not seem particularly impressive compared to, say, the Hubble ultra deep field images where you've got all these beautiful galaxies, I'm showing you some red with some black holes in, which I get it, it's underwhelming, but it's all about what we can infer from this time. And remember, we are talking 13 billion years ago, so give us a little bit of slack. So if we measure a complete picture of hydrogen, then we can know that points back to the Dark Ages. That's when the Dark Ages are happening. As we go through our movie, it's still full, it's still full, it's still full. Oh, there's the first holes. It's the first kind of Swiss cheese we see. And we start measuring that upturn in temperature just before that. And that we call the cosmic dawn. And so from looking at these bubbles, how big they were, how many there were, we can really start to infer what the first sources were, how many first stars, how long did they live, when did the second population of stars come around, when did the first black holes come around. We can tell all of this actually by just looking at these bubbles. So it might be low tech, it might be low production value, but it's incredible in my mind anyway. And it's something we've managed to do actually. So the first detection of the cosmic dawn, at the end of the Dark Ages, the start of the cosmic dawn, was tentatively made in February 2018. I say tentatively because it is yet to be validated by another experiment. This is a really, really hard experiment, and so to really believe the result, we need validation. But everything looks pretty good actually, and what they measured was this change in temperature, which showed the first stars had started. And that was at about 180 million years after the Big Bang. So we've got a marker, we've got a timeline for when the pyramids were built, if you were. That was the square kilometre array that I was talking to you about. That's being built in the next couple of years. I'll go on to that a little bit more in a minute. But the low frequency array in the Netherlands is the telescope which is closest to my heart at the minute, because it's the first telescope that I used, and it's the one that I continue to use today. And again, the technology is a bit underwhelming, if I'm honest, but you've got the antennas here on the top right, and then about 48 of those are under all of these black tarpaulin squares in the background. And I can't remember what my t-shirt says, but I feel like it might be fitting for tonight. Something like, "Ah, well, never mind, a translation. It appears everything in my life is spectacularly going wrong," or something like that. Very British problems, but anyway. So with the LOFAR, we've been observing for about 10 years now, and it's mostly based in the Netherlands, but it also stretches out to a lot of Europe. So we've got stations in France, in Italy, in England, in Wales, all of these different islands, in all of these different places. And so by combining the signals from all of these different times, we're able to tune into this 13 billion years ago. I said that we've been observing for 10 years. So you might ask, well, surely you should have done it by now. Surely you should have come up with something more than just the starting point at 180 million years. The reason is that it's really, really difficult, because when you might have had this question already, but when you have this light from the first stars weaving its way to you, it gets to you at a wavelength of about 2 meters. So we tune in to a wavelength of about 2 meters. Great. Problem is that a lot of stuff, including mobile phones, solar panels, wind farms, all of these things produce interference that is at a wavelength of 2 meters. tons of stuff in our galaxy produces stuff at this wavelength as well. So it's like driving along your road and tuning into lovely, calm, classical radio first stars when suddenly a pirate radio station comes out of nowhere and it starts giving out a very, very different kind of noise. So let's say heavy death metal or something like that. And that's a problem. And it means that our first star signal is buried, just like archaeologically, under about a signal of around 10,000-ish times the size of the first star signal. So that's a huge, huge problem to have to deal with. But it's not one without hope. This is what I do on a day job. And it's that the first star signal is is a different shape. Just as if you were listening to these two stations, you could still tell which part of which signal belonged to each station, because they're playing very different kinds of music. And it's exactly the same with what I do in this. Okay, so we've talked about LOFAR. I'll just be very brief on the square kilometre array, but it's going to be awesome. Whereas LOFAR's got about 3,500-ish antennas, just a couple of thousand anyway. With square kilometre array, we're going to be building 512 stations, so 130,000 antennas in total in the Western Australian desert, because it's really quiet there, which is what you need for big radio experiments that are trying to listen into the early, very quiet signal from the very first stars. And it is an incredible undertaking. It's such an incredible undertaking that the UK government was fighting to get to be one of the first to actually donate money to it, which just shows you, getting money out of our government is no easy thing, but they were jumping on the SKA to give their amount of money in. And it's because it's driving innovation. So this is one of my reasons to care about astronomy if you don't care about astronomy. And it's that, for example, the fibre optic cable that we need to connect all of these antennas together could wrap around the Earth twice. For example, that's a huge amount, and we're driving innovation there because these fibre optic cables cannot move data quick enough for us. We have to delete data, sadly, on the fly as it's happening, because we can't store it all. We're filling about 35,000 DVDs a day, like 1 million laptops per year anyway, and it's a huge amount of data that's overloading computing chips. It's heating them up, so we're driving innovation in how to cool these computer chips. So there's a huge amount of investment in this next generation telescope, the square kilometre array. Like I said, it's turning on in a few years. We'll probably get the first real science results probably in more like 5 years, 6 years, maybe even a bit longer than that. But that's not too long to wait. But while we wait, there are another couple of ways that we can look at these first stars. And I will spend a bit of time on them now. So stellar archaeology is one of my favourites. So I'm just using this to track which slide I'm on. There we go. Stellar archaeology is one of my favourite areas for obvious reasons, just because of the name. And what stellar archaeology is not looking back to the birth of these first stars, but actually kind of looking at the artefacts that got left behind. Now, you might say, well, hang on, how did anything get left behind? Because what you've said is that they lived very, very short lifetimes of 1 million to 100 million years. And that's absolutely true. We think that most of the first stars were very massive and so lived very, very short lifetimes. But we also think, because of lots of simulations now, that these first stars were born with sibling stars. And we think these sibling stars were probably a few of them, and they're probably much lower mass. Such low mass, about 80% the size of our sun, that they would have had a lifetime, or will have a lifetime, of about 13 billion years, which gives them just enough time to still be around today in our local Milky Way. The problem is that these first stars were pristine in nature. So as I've said, you've got these, it's like hanging your beautiful white, washing out into your London backyard. It starts off really lovely. It starts off really metal-free, unpolluted, but it's not too long until everything looks a bit rubbish. And it's the same with the first stars. So whereas they start metal-free, they start pristine, their outer layers very quickly can accrete metals. They can get polluted by their local surroundings. And that happens for 13 billion years. So stellar archaeology is about looking in our backyard, looking at all these different stars and figuring out which ones are actually first stars under all that gunk. And you might look at the wrong one a lot, but you also might now and then get the right one. And the problem is that these stars are really, really well camouflaged. So this only needs to be shown like twice, so we can move on already. But the point is that, you know, they look almost exactly the same as every other star. And the reason I talk a lot about Egyptology at the same time is that there's so many parallels to be drawn, because it's not often mentioned that when Howard Carter found the tomb of Tutankhamun, he didn't just stumble across it. What happened actually was that he bought the permit to dig there from another fellow. Lord Carnarvon paid for it. And he spent 5 years gridding up the entire site and going square by square by square, to the point where even Lord Carnarvon was saying, that's it, I'm cutting you off. You've had enough of my money. You found absolutely nothing. Which point, after 5 years, Howard Carter says, look, just one more dig, and I'm done. Guess what he finds? Which is crazy, but true. So at this point, he finds, you know, the biggest archaeological discovery in history and is rich beyond his wildest dreams. At which point, Lord Carnarvon presumably forgave him pretty quickly. And this is what we're going to do with our first stars. So it's about looking at the entire Milky Way, which is about 250 billion stars, plus or minus 100 billion. That's how many they are. We can't count them. And it's about looking at each of the stars in our grid, or the ones we think are most likely to be metal free. How do you know that? That's another thing that we're struggling with, really. And you look at the light that's being emitted by those stars. And as I said before, if you have metals like carbon, iron, calcium present in your star, for example, you will get absorption lines in your spectra. So you will get dark lines pertaining to those elements. And so what we want to do is we want to find a metal-free star where we really can't really observe those absorption lines at all, or we only observe the tiniest, the faintest grey of a line, if you will, that we can attribute only to pollution. It's hard though, because when you have 250 billion stars to get through, you can spend an awful lot of time looking up the wrong ones. And this is a field that is incredibly interesting. It's incredibly challenging, but I think on the same time scale as, you know, building the squared common array, we're constantly pushing further down. We've found even what we think to be a second generation star, which is a star so old that we think it formed only from one supernovae. What's a supernovae, you ask? So supernovae is the third and final thing that I really want to talk to you about tonight, because it's the third and final way that we can look at this era of the first stars. Now, as I've mentioned, unfortunately, we can't see the light from the first stars themselves because it's just too faint. We can't pick up that signal optically. But if these stars explode in what are some of the brightest explosions in our universe, which is a certain type of supernovae, so supernovae just means the whole star explodes, basically, we do have the option, of the possibility rather, of being able to observe this light with a big space telescope. And so that's what the Americans certainly are going to try and do. It's not the only reason, or by far the most important reason, that they have built this telescope. But what they're going to do is they're going to launch a rocket, and they're going to do what I call an origami space telescope, where over an agonizing month, it folds out its 5 sun shields. It, just like your dining table, if it's got leaves on it, it unfolds each leaf to make a mirror, which is, quite frankly, as I write in the book, just terrifies me, because this has cost $9 billion. $9 billion so far to build. And the idea that it might not unfold correctly over that month, I mean, I should say that, you know, they've tested it so much that the probability of anything going wrong is just minuscule now. But still, I'm a worrier, and it would worry me. Yeah, if we can just, thank you very much. Yeah, $9 billion. So you might be sat there going, we're in the middle of a global pandemic. $9 billion. Well, obviously this $9 billion has been spent over a very long time, because it takes a very long time to think up these experiments. But as one astrophysicist is quoted as saying, and I'm not sure it's true, but anyway, the overlaying message is, he said that that's only what Americans spend on potato chips annually. So actually $9 billion you have to set in the context. And $9 billion, it's fostered huge collaboration. You need expertise from around the world. You're creating new technologies like the folding out the sun shield. Nobody's done that before. Nobody could do that before. And it has applications in defense, in military, in all sorts. Fiber optic cables, all of these things that are coming from the square kilometre array. But just for the science, you know, I won't apologise for saying that I want to do all of this, not to create better fiber optic cable, but because we can look back in time 13 billion years and observe these first stars forming. We can observe them now, we can observe them, their artifacts, and we can observe their deaths as well using the supernovae. And the aim of the game is, of course, to go from we can detect the first stars to we have detected the first stars. And I really do believe that's going to be in the next decade, which is why I wrote a book really to pass on my excitement. And I've touched on a lot of the subjects here, but there's a lot more in there. And at the end of it all, it's incredible science, which I just love, and it's incredible discovery. So wonderful things all around. And thank you so much for your attention. And yeah, there's my book. It's really pretty. So think about buying it for your loved ones or for yourself. Thank you.